In the previous videos, we have seen how to differentiate the inverse trig functions geometrically. Now what we're going to look at here are typical proofs that we would see of the differentiation of these trig functions. So we will work through these proofs and we'll see exactly where they come from. So the typical proof you're going to have here is if we want to find the derivative of the ArcSine function. Now I'll just write the ArcSine function as inverse sine here, so that -1 just tells us this is the inverse sine function. Now the typical way of doing this is that if we were to say that we get the angle here theta from the length x, so we can say that theta is inverse sine x, then we can write it round the other way as x is equal to sine theta. So that is, instead of going from length to angle, we now go from angle to length. And if we take the right hand side of this and we differentiate both sides of it implicitly, then we will have the d by dx of sine of theta is equal to dx by dx. So whenever this is differentiated, we're going to have cos theta here and the d theta by dx, and the right hand side is going to give us a value of 1. So we have used implicit differentiation in order to generate this. Now we will have a look at this a little bit later on in the video. So then we can rearrange this as d theta by dx is equal to 1 upon cos theta. And we can say that the value of our cos theta is nothing other than the root of 1 minus sine squared theta. So there should be a little squared term here. Okay, and that just comes from our cos squared theta plus sine squared theta is equal to 1. So finally, we can say that the derivative of the inverse sine function is 1 upon the root of 1 minus, and the sine squared theta here can simply be replaced up here by the x squared. So we get this here, and we've seen this in the previous video when we looked at differentiating the ArcSine function geometrically. So this is the typical proof that you would tend to see, and there's a similar proof for the arctan and the arccosine, which we will have a look at later or on another video. Now this is the proof that I would tend to use, and it's one I would remember. But when I first seen it, I wasn't very happy with it. It all just looked a bit too neat and tidy, and I had lots of questions. For example, whenever you went to differentiate the inverse sine function, we did it by actually differentiating the sine function implicitly. And I always ask the question, how do you know that that's the way to do it? How do you know that that's going to work and it's going to give you the answer that you're wanting? And it wasn't obvious to me why that was the case. So let's look and we'll see this in a bit more detail, and we'll see why it is we do this and how it is we know is going to work. So let's start off by looking at inverse functions. So if you have the function f of x and g of x, and let's say they are inverse functions, then you can compose these functions and get back to the value of x. So you can say f of g of x is equal to g of f of x just equal to x. Now it's best seen by example. For example, if f of x is equal to x squared and g of x is equal to root x, then the f of g of x tells us that we do the g of x first and we put it into f. So the g of x is root of x, so we do the root of x and then we square it. So the root of x squared is just x. Now we can do it round the other way, the g of f of x. So we do the f of x first, which is x squared, and then we put it into g, which is the root. So it's x squared root, which is just the value of x. So we can see here that whenever we compose these functions, we just end up back with the value of x. Now we can use this in order to generate a nice little identity. So we can see that if we were to take, for example, the value f of g of x, so in effect we've got that f of g of x here is equal to x, and we were to differentiate both sides of this, then we would have d by dx f of g of x is equal to dx by dx. Now the dx by dx here is just a value of 1. And if we were to differentiate a composite function like this, what we get is f derivative of g of x times g derivative of x. Now if you're unsure about this here, then if you go into my channel and you type in chain rule for differentiation, it'll show you how to generate the differentiation of a composed function, and you get this here, and it's quite straightforward. Okay, so have a look at that video. So it means here that what we can do is we can take the g derivative of x is equal to 1 upon f derivative of g of x. Okay, so we're just taking this down. So in this particular example, whenever we differentiate the composition of two functions, whenever the functions are actually inverses of one another, then we get this little identity here. And this is the important identity, and this is why we work through the differentiation of the ArcSine function by first differentiating the actual sine function. So let's finish this off here with a little example, and you can see the power of this. So if we had, for example, we wanted to work out the what happens when we differentiate ln x, and what we could do is we could say, well, rather than differentiating ln x, we will look at the inverse of the function. So the inverse of ln x is e to the x. So that means that we can, from the above here, we can write the g derivative of x, okay, so this is the differentiating ln x, is going to be 1 upon f derivative of g of x. So it's going to be 1 upon, well, the f derivative, well, whenever you differentiate e of x, you get e of x. So it's going to be e of, and it's g of x, which is ln x. So it's e to the ln x. But e to the ln x are just inverses, okay? So all you're just going to be left with here is the value of x, which is 1 upon x. So it means whenever we differentiate ln x, we get 1 upon x. And this is a nice, neat little proof of this differentiation, and this is the one here that I tend to remember. So let's continue with this, and finally we will look at the same type of example here, but we'll use the ArcSine x. Now we can replace the example below here with the sine and inverse sine. So we have x is equal to sine of theta, that is, we go from angle to length, or we can have theta is equal to inverse sine x, that is, we go from length to angle. And we can generate the functions x is equal to f of theta, such that it equals sine of theta, and theta is equal to g of x, such that it equals inverse sine of x. And we can see here that these are inverses. If we have the sine of the inverse sine of x, well, the inverse sine of x is just the value of theta. So that's sine of theta, which is just equal to the value of x. Equivalently, we can have the inverse sine of the sine of theta. Well, the sine of theta here is just x, so the inverse sine of x is just equal to the value of theta. So we can see here that these are indeed inverses. And then we can use the equation above here because we know they're inverses, so we can say the g derivative of x is 1 upon f derivative of g of x. So that's 1 upon, well, the f derivative, well, f is equal to sine, so that will change to cosine. So it's going to be the cosine of the g of x, Well, g of x is just inverse sine, so it's the cosine of the inverse sine. So we can see here then that the inverse sine of x is just the angle theta. So that's just the cos of theta, which is equal to 1 upon the root of 1 minus x squared. So that's us just about finished. There is one final way that we can look at this that is a little bit closer to the geometric proof, and we will look at that next. Now we can rewrite this line here in this form, and in this form there's a direct relationship to our original geometric derivation of the derivative of the ArcSine function. So the g derivative of x is nothing other than d theta by dx. And we can see that from above. We have the g of x is equal to the arcsine x. That is, we go from length to angle. So if we have a small change in length, we'll generate a small change in angle. And that's what this says, d theta by dx. That is, a small change in length will give us a small change in angle. And that is equal to 1 upon f derivative of the g of x. Now, g of x here is nothing other than theta, so it's f derivative of theta. And you can see again from above that x is equal to sine of theta. So that means that a small change in angle will give us a small change in length x. And that's what we've got here, dx by d theta. That is, a small change in angle will give us a small change in x. But from our original diagram, this is at angle theta here. The dx is this height here, h, and we have our d theta. So the dx by d theta is nothing other than the cos of this angle theta. And that is 1 upon the root of 1 minus x squared. Now we know that finding the derivative of the arcsine function using implicit differentiation works, because the implicit differentiation is nothing other than our chain rule, and it's applied to functions which are inverse. So that's all for this video. In the next video we will finish off by looking at the derivation of the arc cosine and the arctan function using this implicit method. So thank you for listening. I'll get you on the next video. Goodbye.